Hello everyone and welcome back to this NPTEL lecture series on cycloaddition. So this is the 7th lecture of this series. In the last lecture we briefly talked about intramolecular Diels-Alder reaction, particularly type 1 Diels-Alder reaction. So in type 1 Diels-Alder reaction, as you know, the dienophile is attached to carbon number 1 of the diene, and that when it undergoes IMDA type 1 Diels-Alder reaction, it gives normally the fused bicyclic system. So today what we will do, we will move to type 2 intramolecular Diels-Alder reaction. So what is type 2 intramolecular Diels-Alder reaction? So in the case of type 2 intramolecular Diels-Alder reaction, the dienophile is attached to carbon number 2 of the diene. So you have seen earlier when it was attached to carbon number 1 and it gave the fused bicyclic system. Okay. Now when it is attached to carbon number 2, then there are two possibilities. One, you can write the way I have written. The other possibility is you can rotate the dienophile and you can draw like this. So this in principle will give you a 1,3 bicyclic, but it is bridged system, and here what you will get is 1,4 bicyclic, again fused system. In the case of intermolecular Diels-Alder reaction, we have discussed in details that when you have substituents attached to the dienophile, and normally the expected product is either 1,2 or 1,4. But if you look at the intramolecular Diels-Alder reaction type 2, you will mostly get 1,3. Okay, 1,3 is the major product. As you know, 1,4 from structure point of view, it is not that easy to get 1,4. So what you get is a bridged bicyclic system in intramolecular Diels-Alder reaction type 2. Essentially you will get is the bridged bicyclic system. So the intramolecular type 2 Diels-Alder reaction is not that easy. One, it requires very high temperature. Second, if you look at the product, you will see a double bond at bridgehead position. And we know, according to Brett's rule, a double bond cannot be at the bridgehead position. But still, this intramolecular Diels-Alder reaction type 2 undergoes to form such bridged bicyclic system. Okay, let us go ahead and then discuss more such intramolecular type 2 Diels-Alder reaction atoms. So when we talk about type 2 IMDA reaction, it was accidentally observed when Kenneth Shaw wanted to do a 3,3 sigmatropic rearrangement on this substrate. As you can see here, it's a 1,5 diene. So 1,5 dienes are well known to undergo 3,3 sigmatropic rearrangement, and this was the expected product. So it is a cope rearrangement product, but what he actually got was this diene. Okay, you can see huge difference between the expected and observed product. In the case of expected product, you have two cyclobutene rings connected by an ethano bridge, whereas here he got a bicyclo-2,2,2 octane system with two exocyclic double bonds. So what actually had happened in this reaction? So as expected, the first step it underwent a cope rearrangement, that is 3,3 sigmatropic rearrangement to get the expected product, but it did not stop at that stage. And as you can see here, since it has two cyclobutene rings, cyclobutene ring is well known. If you heat it, it can undergo a thermal electrocyclic ring opening reaction. So that is what happened. So it underwent an electrocyclic ring opening to give two dienes. connected again by the ethanol bridge. And these dienes can be redrawn like this. So when you redraw, you can see this dienophile is attached to carbon number 2 of the diene. So this underwent an intramolecular type 2 Diels-Alder reaction to give this bicyclic compound, and it does not end or it does not stop there. What happened? This also can be redrawn. Okay, for the simplicity, you have redrawn like this. When you look at this molecule, again you can see this can undergo another 3 sigma tropic rearrangement. So 1, 1, 2, 3, 1, 2, 3. So if this undergoes another 3 sigma tropic rearrangement, and you will get this bicyclic compound. So basically, if you look at this whole reaction, it went through a cope rearrangement, a 4-pi electrocyclic ring opening, and type 2 IMDA reaction, again a 3 cope rearrangement. So 4 important reactions took place to convert this compound to this one. Okay. So one of the reaction is the type 2 intramolecular Diels-Alder reaction. So that is how type 2 intramolecular Diels-Alder reaction came into force. So what are the various possibilities? Initially, these type 2 intramolecular Diels-Alder reactions were done at gas phase because it requires very high temperature. So mostly this reaction was done at a gas phase about 400 degree centigrade. So for example, take this compound. So if you heat it around 400 degrees, you also can redraw this molecule this way. So just rotate it by 180 degrees, so you get this. Now this is the dienophile and this is the diene which is attached to carbon number 2, and it undergoes an intramolecular type 2 Diels-Alder reaction to give this compound. And if you have electron withdrawing substituent, as you know, any Diels-Alder reaction, particularly normal Diels-Alder reaction, if you have an electron withdrawing group at dienophile, the reaction is facile. So when you have electron withdrawing carbonyl group, then this can undergo an intramolecular type 2 Diels-Alder reaction to give this bicyclic compound. And here in both the cases, it is bicyclo 3-3-1 system. 1, 2, 3, 1, 2, 3. So it is bicyclo 3-3-1 system. So one can also get a bicyclo 4-3-1 system. 1, 2, 3, 4, 1, 2, 3. So depending on the tether, actually this is normally we call it as tether or linker, which is connecting the dienophile and the diene. The tether which connects the diene and the dienophile determines the ring size of the newly formed bicyclic compound. Okay. So this was earlier done after the serendipitous observation of type 2 IMDA Diels-Alder reaction. So then these reactions were carried out in heating under refluxing condition in solvents. So one can also do this with electron withdrawing substituent at the terminal carbon. So in particularly in this case, you have the carbonyl group inside. Here the electron withdrawing group is at the terminal carbon. So this also can undergo an intramolecular Diels-Alder reaction to give bicyclic compound. So then how to carry out this reaction? As you know, you have to heat it at high temperature, and at the same time this is an intramolecular reaction. So obviously this reaction should be done under very dilute condition. So you can dissolve it in high boiling solvent and do it under very high dilute condition. So the same thing can be done in solution phase. So that is how such reactions were repeated in solvents and to get exactly the same product or products which were observed in gas phase reaction. Later, to reduce the temperature required for such intramolecular type 2 Diels-Alder reaction, what people did was to use Lewis acid. When you use Lewis acid in Diels-Alder reaction, what happens is it brings down the energy gap between the HOMO of the diene and LUMO of the dienophile. So, it coordinates with the carbonyl group or electron withdrawing group of the dienophile, and it brings down the energy of LUMO, so that the HOMO-LUMO energy gap comes down automatically. As a result, the temperature required for Lewis acid catalyzed Diels-Alder reaction is very low. Many times you can do this reaction at room temperature or even at sub-room temperature. So, for example, if you take this substrate and then treat with Lewis acid like diethyl aluminum chloride, you can do this reaction at room temperature, and within 1 hour you get this bicyclic compound. Likewise, if you replace this carbon by an oxygen, the same thing can be done at room temperature with diethyl aluminum chloride to give this bicyclic compound. So, from 400 degrees you can bring it down to room temperature to carry out the same IMDA type 2 reaction by using Lewis acid. And one can also have a triple bond as the dienophile. For example, this substrate, if you do this with diethyl aluminum chloride, gives the bicyclic compound. Now you can see, so this is a very nice intermediate having a cyclohexadiene. Normally when you have cyclohexadiene, we always think about using Birch reaction. So now one can also use intramolecular type 2 Diels-Alder reaction to generate such dienes, and more importantly you can see the substituents are 1,3 with respect to the diene. So how about the stereochemical outcome? So we discussed in details the intermolecular Diels-Alder reaction and how the stereochemical outcome and regiochemical outcome of intermolecular Diels-Alder reaction. How about the stereochemical outcome of IMDA type 2? We already discussed that this is a unique Diels-Alder reaction where you get a double bond, which is against Brett's rule. So accordingly the second ring, so in addition to the 6-membered ring, as you know, when you do a Diels-Alder reaction you get a cyclohexene ring, but the size of the second ring decides whether this reaction will go or not. So for example, if you have a carbonyl group part of the second ring, then this N should be 6 or 7. Minimum it should be 6. However, if the carbonyl group is part of the 6-membered ring, here you can see the carbonyl group is part of the 6-membered ring, then N could be minimum 4. So 4 means this is 4, then you have 5, 6, 7, or in other words the second ring should be 7-membered ring. Whereas if the carbonyl group is part of the second ring, then it should be minimum 9-membered ring. Okay, then only this reaction will work. And coming to the stereochemistry, what was proposed is there are two possibilities. One is the tether. The tether is endo to the diene, okay, and the other possibility is tether is exo to the diene, okay, and the major product we get is the tether endo product. See, for example, if you have like this system, this is the tether, okay. Now whether this tether and then diene are in the same side or opposite side. So that is what matters. In this case it is opposite side, so that means tether exo. Now you can see here X is inside, here X is outside. That means if X is outside, tether is inside. If X is inside, tether is outside. So in the case of IMDA type 2, the tether should be inside the ring. So this is called tether endo product. So, this is what is explained here. The tether is endo and hydrogen is outside. Here you can see tether is outside, in this case tether is outside and hydrogen is inside. So, that means tether is exo, okay, but the major product is tether endo product. So, let us discuss some more examples. So, if you take a diene with a dienophile having a carbonyl group, so this can undergo intramolecular Diels-Alder reaction type 2. As you can see here, the tether endo product. So, this is the carbonyl group and the whole tether is endo, and that means this hydrogen is exo. Likewise, in this case also the tether has a phenyl group. So, this hydrogen also will be beta. And this is another interesting example where the ester group is outside the ring, whereas in both these cases the electron withdrawing carbonyl groups are inside the ring or part of the 7-membered ring or 8-membered ring. Here the ester group, which is electron withdrawing, is outside the ring. So, you can see it is at the Bridget carbon. One of the interesting aspect of this type 2 Diels-Alder reaction cycloadducts is you can convert this bridged bicyclic compound into fused bicyclic compound in 2 steps. Normally, when you do type 1 intramolecular Diels-Alder reaction, you get fused bicyclic system. So, in this case you get bridged bicyclic system, but however, by using a couple of synthetic transformations, one can convert this bicyclic bridge system to fused system. So, this is the product you get when you do a type 2 intramolecular Diels-Alder reaction. Now, you can see this has a double bond. The cyclohexene double bond, if you do ozonolysis, you get a keto-aldehyde, okay, keto and aldehyde. Now, if you treat with base, then you can see it can generate anion and form enolate, and that can add to the aldehyde, and followed by elimination of water, one can get a cycloalkenone. So, basically what you have done in this 2-step process is the bridged bicyclic system has been converted into fused bicyclic system. Okay. A specific example, so if you take this triene and then do a Diels-Alder reaction, you get this bicyclic diene. Now, if you do ozonolysis, you get ketoaldehyde, and this upon treatment with either acid or base, you get the bicyclic compound, and one is 5-membered ring, other one is 8-membered ring. So, the 8-membered ring is coming out from the tether. Another example, you do the Diels-Alder reaction, and what is different in this case is you have another methyl group. So, if you do ozonolysis, so here you will get a diketone, unlike the last case where you got ketoaldehyde, here you get diketone. So, once you have diketone, then upon treatment with either acid or base, you get bicyclic compound, and here this is a tetrasubstituted bicyclic. Like intermolecular Diels-Alder reaction, in the case of intramolecular Diels-Alder reaction also, one can replace one or more of the carbon atoms by heteroatom. So, then such reactions are called type 1 hetero intramolecular Diels-Alder reaction or type 2 hetero intramolecular Diels-Alder reaction. See, for example, here you can see the tether is here, the tether is attached to carbon number 2, and the dienophile, here you cannot see the dienophile, that is the double bond, but when you heat it, then the elimination of the acetic acid in situ will generate the dienophile. Now, so this will undergo intramolecular type 2 Diels-Alder reaction to form a very interesting bicyclic compound having a nitrogen at the Bridget position. So, this is a very clever way to make such bicyclic system with nitrogen at the Bridget position. So, another example, so this is also a very simple intramolecular type 2 Diels-Alder reaction, but Here there is no heteroatom, but in principle one can use heteroatom either here or here to introduce or have a heteroatom in the second ring. Okay, we will see more examples and you will find many such reactions are known. So, what are the dienophiles we have used? We have used simple alkene, and then we also used imine, and we also used electron deficient alkene having a carbonyl group or ester as electron withdrawing group in the dienophile. So, now how about using allene? If you use allene, whether such substrates can undergo type 2 intramolecular Diels-Alder reaction? Yes, it can undergo. So, when you heat this substrate, it can in principle undergo intramolecular type 2 Diels-Alder reaction to give this compound as well as this one. Can you guess how the second product was formed? This I know easy to, this is as a result of intramolecular type 2 Diels-Alder reaction, but can you see how this product is formed from this? The first ring is 5-membered ring, so that means you can see 1, 2, 3, 4, 5. So, this is the 5-membered ring, and this alkene undergoes a 2+2 cycloaddition reaction. So, this is nothing but intramolecular 2+2 to give this product. So, now the same compound, what you do not have is, here there is no oxygen, but here you have an electron withdrawing group. So, what will you get? Again you can get the intramolecular Diels-Alder reaction type 2 product. In addition, you also can get the 2+2 cycloaddition product. Okay. So, this is another example where you can see where the heteroatom is part of the dienophile and also it is part of the second ring. Okay. So, this is what you get, and you also get a little bit of this minor product. Okay. Try to write mechanism for this particular compound. Okay. So, coming to the mechanism, as I told, this can be formed by an intramolecular 2+2 cycloaddition reaction, and the IMDA type 2 will give this product. And so, now this can also undergo a 3,3 sigmatropic rearrangement. So, if this undergoes 3,3 sigmatropic rearrangement, then you will get another interesting bicyclic compound, and here as I said, first is intramolecular type 2. Okay. So, there are two double bonds in the allene, A and B. Suppose if A undergoes intramolecular type 2, then you get this product, and if B undergoes intramolecular type 2, you get this product, and this is the intramolecular 2+2 cycloaddition product, which in principle can undergo a 3,3 sigmatropic rearrangement to give another bicyclic compound, and this also can undergo another 3,3 sigmatropic rearrangement to give this one. Okay. So, when you have allene, there are many possibilities to get the corresponding bicyclic system. So, here is an example where you generate allene in situ. When you have a propargyl system and then treat with potassium tertiary butoxide, so this can in situ generate this allene, and once you have this allene, then this can undergo intramolecular Diels-Alder reaction to get this tricyclic compound. And if you treat this with camphor sulfonic acid and water, then water addition will take place to this enol ether to form a lactol, and then the lactol can be oxidized with PDC to get the corresponding lactone. So, my question here, as in the title, is whether this is type 1 intramolecular Diels-Alder reaction or type 2 intramolecular Diels-Alder reaction. This is for you, and you can answer this question. Then, as I said, heteroatom has been successfully used in type 2 intramolecular Diels-Alder reaction. And how one can control this regiochemistry with the tether. Tether plays a very important role not only in regiochemistry but also in stereochemistry. So, how do you attach that tether to the diene? See, for example, if you have this vinyl magnesium chloride and if you quench with this corresponding silyl chloride, so now you have a silyl methyl chloride. Okay. This chloride, upon treatment with magnesium, this will form a Grignard. Once it forms a Grignard, you quench with formaldehyde and that will give you the corresponding primary alcohol. So, this primary alcohol then you can couple with cinnamic acid to form this cinnamate ester. Now, you can see here you have diene and you have dienophile and this is connected to carbon number 2 of the diene. This in principle can undergo intramolecular type 2 Diels-Alder reaction to give this very interesting bicyclic compound. So, the advantage is once you have this, you can hydrolyze this lactone with methanol. So, you get ester at this carbon. You can see, so once you hydrolyze, this will be alcohol. So, this is the first step. So, when you treat with methanol, so it esterifies, the lactone gets hydrolyzed to get ester and alcohol. So, now this upon treatment with acetic anhydride, you get the corresponding acetate. Now, if you treat with TBOF and MCBBA, you get the corresponding ketone. Try to find out mechanism for the last two steps, how the vinyl silyl ether gets hydrolyzed and then get oxidized to corresponding ketone. One can also use alpha beta unsaturated ketone to make the diene. So, if you take an enone like this, then treatment with LDA and diphenyl silyl dichloride, so you get the corresponding enol silyl ether, but also the silyl group as a chloride. So, this means you can treat with any alcohol in the presence of base. So, now the alcohol can be protected as this silyl ether. So, this is what happens. So, now you can see the diene is ready and the dienophile is attached. Now, if you heat it, you will get this tricyclic skeleton. If you hydrolyze and then cleave this SiO bond, then again you will get a bicyclic compound where you will have this ester and here you will have a ketone. Yeah. A similar example, okay, if you do intramolecular type 2 Diels-Alder reaction, so you get the tricyclic compound. Now, again if you hydrolyze with HCl and then treatment with potassium carbonate methanol, so you get this bicyclic compound. So, this intramolecular Diels-Alder reaction has been successfully used to construct the core structure of many natural products, and also people have used in the total synthesis of natural products. So, let us discuss a few examples. For example, J.S. Yadav from IICT, he has cleverly exploited this intramolecular type 2 Diels-Alder reaction in the synthesis of the core structure, ABC ring structure of Taxol. So, this substrate has smoothly underwent an intramolecular Diels-Alder reaction to give this tricyclic compound. This upon reduction of the carbonyl group and protection of the resultant hydroxyl as TBS ether gave this compound. Now, this tricyclic compound upon treatment with butyl lithium underwent Wittig rearrangement to give this tricyclic compound. So, basically what happens when you treat with butyl lithium, it generates anion and it attacks this carbon and breaks this CO bond. So, that is how he constructed this the middle 8-membered ring of Taxol using this nice combination of intramolecular Diels-Alder reaction type 2 and Wittig rearrangement. Kenneth Shaw used intramolecular Diels-Alder reaction type 2. He started from cyclohexane 1,3-dione. So, then he alkylated with 2,3-dibromopropane and followed by diazomethane treatment gave this enol ether. Now, addition of this Grignard reagent to this carbonyl group followed by hydrolysis, you could get this cyclohexenone, and in the cyclohexenone you can see the diene and dienophile attached at carbon 1 and 2 here. So, then he protected the ketone as ketol, then exchanged this bromine with butyllithium and quenched with DMF to introduce the aldehyde group. So, this underwent a smooth intramolecular Diels-Alder reaction to give the corresponding tricyclic compound. One can also use masked diene, because sometimes when you use these dienes it can undergo polymerization. So, Jeffrey Winkler has cleverly used a masked diene in intramolecular Diels-Alder reaction type 2. Kenneth Shaw also has used a masked diene. In this case Shaw has used a cyclopropane. Okay. So, now if you take this heavily substituted cyclopropane with bases like 2,4,6 quolidine, so that undergoes elimination of HBr to generate this diene. Once it generates, automatically it undergoes intramolecular Diels-Alder reaction to give this tricyclic core structure of Taxol. And people also, as I said, can use other masked diene, for example sulfolene. Okay. Sulfolene, if you heat it, it can undergo any sulfolene. If you heat it, it can undergo extrusion of sulfur dioxide to generate diene. So, here what happened was the extrusion of sulfur dioxide gave this diene, and that diene underwent intramolecular Diels-Alder reaction with the dienophile to give this interesting bicyclic compound. As I said, Winkler used sulfolene as the precursor for intramolecular Diels-Alder reaction, and when he used this sulfolene, first he treated with sodium hexamethyl disalicide. So, that generated anion here, and you can quench with the corresponding bromide to introduce the diene on the left hand side and potential masked diene on the right hand side. So, when he reflexed with toluene, it generated this diene, and now he treated with divinyl ketone. Okay, you can see here there are 2 double bonds. Okay, and the first intramolecular Diels-Alder reaction took place between this diene and the double bond of this divinyl ketone to give this intermediate, and then he has to use a little stronger acid like BF3 ethyrate to close this ring using the intramolecular Diels-Alder reaction. And people also use this in other natural product synthesis. For example, this alpha beta ancestor ketone, upon treatment with potassium hexamethyl disalicide, it forms the enolate, and then the enolate was quenched with diphenylsilyl dichloride, and that upon protection with this alcohol. So, you can see here there is a diene and there is a dienophile. Okay. This upon intramolecular Diels-Alder reaction gives a quite complex structure, where you can clearly see there are 4 rings: ring number 1, ring number 2, ring number 3, and a macrocycle ring 4, and highly congested with many chiral centers. So, this is possible only through such intramolecular Diels-Alder reaction, and this is the key reaction in the total synthesis of adrenosterone and this intermediate was converted into adrenosterone in few steps. So we will stop here today, and then tomorrow we will talk about retro Diels-Alder reaction, Alder-Rickert reaction, and so on. Okay, so thank you.